So here we are in chapter 20. This is on electrochemistry. This is going to give us an opportunity to review a lot of the topics that we've already covered in chemistry throughout the year. So we'll be working first with our friend oxidation states. We'll go over those. After a quick review of the oxidation states, we're going to go on to balancing equations using a redox method. Oxidation numbers are going to correspond to the oxidation states of each of the atoms in a given compound, whether it's, if it's bonded to something, if it's not bonded to something, then as it is. So in the equation here, where we've got zinc reacting with probably a solution of hydrochloric acid, the zinc starts out neutral, so it's 0, so it's neutral zinc. The hydrogen is in the 1+ state, so it's lost an electron. And then in the process of the reaction, the zinc is going to force the hydrogen to take its electrons, the zinc being more reactive than the hydrogen. And therefore, the zinc will go to a 2+ state, and the hydrogen will become neutral. Now, if we think about this in terms of the macroscopic view of this and the microscopic view, on the macroscopic view, we would see a solution here of probably hydrochloric acid. You can see the zinc on the spatula here being added to the hydrochloric acid. And again, the zinc here is not charged. It's electrically neutral. And now it's going to be put into the hydrochloric acid. You get bubbling, which is the hydrogen gas being given off. And again, that's going to be neutral, as the zinc has forced the hydrogen atoms to take their electrons. And so you can get an idea there, and obviously the chloride ions stay the same in negative charge. There's some set rules that we use to assign oxidation numbers. These can be found in your book as well. So the first rule that we have is that elements in the elemental form always have an oxidation number of 0. So it would be zinc in the last example, or hydrogen. The oxidation number of a monatomic ion is the same as its charge. So again, that would be the same as the hydrogen ion H+, or the zinc ion, the Zn2+. Rule number 3, nonmetals tend to have a negative oxidation number, although some are positive in certain compounds or ions. So we'll see a couple of examples of those. Oxygen normally has a oxidation number of -2, except in peroxides. In the peroxide ion, it has an oxidation number of -1. Hydrogen will have an oxidation number of -1 when it's bonded to a metal, and +1 when it's bonded to a nonmetal. Fluorine always has an oxidation number of -1. The other halogens have an oxidation number of -1 when they're negative, but they can also have a positive oxidation number when they are combined with oxygen, for instance, in the oxyanions. So chlorate, chlorite, hypochlorite, and perchlorate. Number 4, the sum of the oxidation numbers in a neutral compound is always 0. And the sum of the oxidation numbers in a polyatomic ion is equal to the charge on the ion. A couple of examples of these. So I mentioned perhaps the perchlorate ion, so Cl O4 with a minus charge. Again, if we assume that oxygen is going to have a 2- charge, so we always start there. We have 4 oxygens, so there's 4 2- charges there. We know that the overall ion has to have a minus charge, so together with all the oxygens, we have 8 minuses. Overall, we want a -1 charge, so that means in this situation, the chlorine is a 7+. Another one we can look at would be dichromate, Cr2O7 with a 2-. Again, if we assume the oxygen's a 2-, and in this case we have 7 of those, so that would be a total of 14 minuses. We want the overall ion to have a 2- charge, So that means that total for the chromium, we want to have 12 pluses. So that would be 2 times 6 plus for the chromium. So the chromiums in this compound are a 6 plus oxidation state. Now, balancing redox or oxidation reduction reactions. This is going to be slightly different than the method that we used when we just balanced ordinary chemical reactions. It's going to be a little bit more involved. There's definitely a system that we have to follow in order to do this. We're going to use what's called the half reaction method. Now, this works only on paper. What we're going to do is we're going to treat the oxidation and the reduction reaction as two separate processes. We're going to balance each of these half reactions alone and then combine them together at the end to get the balanced equation for the overall reaction. All right, as with the oxidation numbers, these rules or steps that we're going to use can be found in your book. The first step is to assign the oxidation numbers of each element to determine what is being oxidized and what's being reduced. And we'll go through an example of this in just a minute after we go through the rules. Number two, we're going to write the oxidation and reduction half reactions. Number three, we're going to go through and balance each half reaction. Now, when we do this, there's some sub-steps we have to go through. First, we're going to balance the elements other than hydrogen and oxygen. We're going to balance oxygen by adding water to the side that we need the oxygen on. We're going to balance hydrogens by adding H plus to the side that needs the hydrogen. And we're going to balance the charge at the end by adding electrons. Now, keep in mind that we're assuming that, or we're not assuming, but these reactions have to happen in acid. It's a slightly different procedure if they're happening in base, but the balancing of the hydrogen by adding H plus basically requires that we perform this reaction in acid. And it's not too unusual for oxidation reduction reactions. Number four, then, after we have each individual half reaction balanced, we're going to multiply the half reactions by integers so that the electrons gained and the electrons lost are the same. This is conservation of charge. And again, we'll see an example of what that looks like. We're going to add the two half reactions together, subtracting things that occur on both sides. And then we're going to kind of double check our work and make sure that the equation is balanced according to mass and that it's balanced according to charge. Here we have a typical oxidation reduction titration reaction. So we're adding permanganate. So this is the solution that's in the burette, the purple solution, and it's being added to a solution of oxalate, the C2O4 2-. And the product of this reaction is the manganese 2+ ion and carbon dioxide. So we're going to attempt to balance this equation using this redox method. Step number one, we're going to assign oxidation numbers to determine what's being oxidized and what's being reduced. So again, if we go with oxygen as a 2-, so there's 2- for the oxygen, and that gives us 8 minuses, but we want it overall to be -1, so the manganese here is a 7+. And then if we look at the oxalate ion, in this one, the carbon, again, if we go with 2- for the oxygen, there's 4 of them, that's 8 minuses. We want it to be overall a 2-, so that means the 2 carbons have to total 6+. So each carbon is going to be a 3+, there. And then if we go to the other side of the equation, we see that the manganese has gone down to a 2+, right? So the manganese has gained electrons to do that. And the carbon has gone to a 4+, so it's lost electrons to do that. Remember our saying, Leo the lion goes grr, right? To lose electrons, let's put that up here for us. Leo the lion goes grr. Right? So lose electrons, oxidation, gain electrons, reduction. So we can see that the manganese going from a 7 plus to a 2 plus has lost, has gained electrons, so that's the part that's reduced. And the carbon dioxide going from a 3 plus to a 4 plus has lost electrons, so that was oxidized. Step number 2, we're going to go ahead and write the oxidation and reduction half reactions. So our oxidation reaction, again, is we lose electrons, so the oxalate ion. So we got C2O4 2 minus going to CO2. And I'm going to move that over, I think, to the middle here. And so this is the oxidation reaction. And our reduction reaction, our part that gained electrons, is the MnO4 minus going to Mn2 plus. All right, so there's our oxidation and our reduction half reactions. Now that we have the two half reactions, we're going to balance each one of these. Now I'm going to start with the reduction half reaction, since it's underneath here. And I'm going to follow the steps to number 3. So the first thing says to balance the elements other than hydrogen and oxygen. So the only other element is the manganese, and so I have one manganese on the left and one on the right, so that means that element is balanced. Now I'm going to go ahead and balance oxygen by adding water. So I need oxygen over on the right-hand side. So I'm going to take my manganese, or my permanganate, and over on the right-hand side, I'm going to put 4 water molecules to balance out the 4 oxygens in the permanganate. And now I'm going to balance the hydrogen by adding hydrogen ions. So when I added the water, I added 8 hydrogens. So I'm going to put 8 hydrogens over on the other side. Just 8 hydrogen ions. And then I've got to balance the charge by adding electrons. So right now I have, 8 positives on the left and 1 negative. So that's going to be a total of 7 positives on the left-hand side, and I have 2 positives on the right. So I'm going to have to add 5 electrons to the left side to balance that out. So my 5 electrons, my 8 protons, and the -1 charge on the permanganate add up to a 2 plus. And then over on the right, I've got my manganese that's got a 2 plus. So I've now successfully balanced the reduction half reaction. All right, let me go up here, and we'll copy the oxidation half reaction. Bring that down. All right, so keep our rules here. So we're going to balance the elements other than hydrogen and oxygen. So here we do have to balance the carbons. So if I put a 2 in front of the CO2, that's going to do a pretty good job there balancing the carbons. So I have 2 carbons on the left, 2 on the right. I'm going to balance oxygen by adding water. So I have currently 4 oxygens on the left and 4 on the right. So I actually don't have to do anything with oxygen. And there's no hydrogen in the compounds either, so I don't have to do anything with either one of those. What about looking at the charge? Well, if I look at the charge, I have a 2 minus charge on the left with the oxalate ion. And over on the right, I've got a neutral carbon dioxide. So to get 2 negatives over there, I'm going to have to add 2 electrons. Now remember, oxidation moves electrons, so it's good. It's good that we have oxygens being lost or given off on that side there. Now let's get rid of this part here. So here I put the two half reactions together, and we're going to use rule number 4, which says to multiply the half reactions by integers so that the electrons gained is equal to the electrons lost. So let's see. So we have 5 electrons gained in our reduction half reaction and 2 electrons lost in our oxidation half reaction. So our lowest common multiple would be 10. Right, so to get the loss and gain of electrons to be equal, we're going to multiply the reduction half reaction by 2 and the oxidation half reaction by 5. Now we're going to add the reactions together, making sure that we take off things that appear on both sides. And so I'll just be a little careful with my math here. Maybe I'll go through and do the balancing here first. So if we multiply the 2 through, I have 10 electrons, I have 16 hydrogens, I'll have 2 of the manganese ion, and 8 waters. And if I multiply this one through by 5, I get 5 of the oxalates, I get 10 of the carbon dioxide, and 10 electrons. So before I add them together, let's cancel things out. So we have our electrons canceling out, which is a good thing. And it looks like that's about all that we're going to cancel out in this reaction. So I'm going to go ahead and write out the things that are left over. So on the reactant side, I have 16 hydrogen ions. I have 2, sorry, I should have put that in there, 2 of the permanganates. I have 5 of the oxalate ions. So those are all my reactants. And then on my product side, I'm going to have 2 of the manganese ions, 8 water molecules, and 10 molecules of carbon dioxide. Now we're going to go through and just double check and make sure we did everything correctly. So I think you'll find that we have 16 hydrogens on both sides, 2 of the manganese, we have 28 oxygen, and it looks like 10 carbon on both sides. So we're balanced according to mass, and then the other thing we have is to make sure that we're balanced according to charge, and we have 16 positives, 2 negatives, and then another 10 negatives, so that's 12 negatives, 16 positives, which gives us a 4 plus on the left, and then over on the right we have 2 manganese ions, which also gives us a 4 plus on the right side. So hopefully we have done everything correctly then in balancing this equation. Now we also see oxidation reduction reactions happening in base. If we have a reaction happening in base, instead of having hydrogen ion to work with in the equation, we have hydroxide ion to work with in the equation. Now, the easiest way to do this by the half reaction method is to go ahead and do the process for the that you went through for the acid, but then we're going to add hydroxide to both sides of each half reaction to balance out the hydrogen. Now, in the first one, so I'm going to do this in red. The first one, we've got 8 hydrogens on the left, so we're going to have to add 8 hydroxides on the left. And yeah, we have to keep it balanced, so we're going to add 8 hydroxides to the right as well. Now, the second equation, we aren't going to have to do anything with that one because there's no hydrogen ion in that one. So I'm going to go ahead and rewrite that first reaction with the hydroxides that we've added. Now, what you have happen here is those hydroxides and those hydrogens are going to basically combine to form water. So we still have our 5 electrons, but now over on this side we're going to have 8 water molecules instead. We still have our permanganate, and then over on the right we have our manganese ion, 4 waters, and now the 8 hydroxides that we added on. So you see all that this did really was add hydroxide to the opposite side, and then the hydroxides and the hydrogen combined to make more water. Now what we can do then is reduce this. Reduce this 8 down to 4 and eliminate the 4 waters on that side. So now when we add these together, sorry, forgot we need to multiply through, sorry, not by 10. Multiply this through by 2, and this through by 5. And then we'll add them together. And again, let me just go through and change the coefficients here so that we don't get anything messed up. So this will be 10 electrons instead. This will be 8 water molecules, 2 permanganates, 2 manganese ions, and 16 hydroxides. And up top, we multiply by 5. We get 5 oxalates, 10 carbon dioxides, and 10 electrons. We go through and cancel things out. Again, our 10 electrons will cancel out on each side. And I believe that's all we're going to get canceling. Again, in this case, now we'll rewrite the equation. We'll add the equations together down below. So I have 5 of the oxalate ions on the left from the first equation, and then I'm going to have 8 water molecules. I'm going to have 2 of the permanganate, and then over on the right we'll form 10 carbon dioxide molecules, 2 of the manganese ions, and we have left 16 hydroxide ions. Right. And again, we can go through and double check, and I think you'll see that we balanced everything, all the elements out, and we have, let's see, 10 negatives, 12 negatives on the left, and is that right? 12 negatives on the left, and 16 negatives, 4 positives, and 12 negatives on the right. So we balance both by charge and by number of ions. I think you'll agree that if we tried to work through this with a guess and check, even if we knew that we could add hydroxide and water, that both the reaction that happens in base and the reaction that happens in acid, we wouldn't be able to do by just our normal guess and check method. So we need to have this type of strategy available to us if we're balancing redox reactions.